Okay, this is part 2 of chapter 6 on proof by contradiction. And here is what we want to prove, that the square root of 3 is irrational. So again, we know we're going to use a proof by contradiction. It's pretty easy to negate that statement. So suppose the square root of 3 is rational. Well, just like before, then the square root of 3 equals a over b for some integers a and b. And we can square both sides. And what do we get? We get 3 equals a squared over b squared, or 3b squared equals a squared. Now, we're going to take a slightly different tack to do this, but let's first consider the prime factorization of a. Now, what I'm going to claim is that every prime number that is in the prime factorization of a shows up in a squared an even number of times, twice. So every prime in a squared occurs an even number of times. And it's worth noting 0 is even. So every prime number that's in a squared occurs an even number of times. So a squared contains an even number of 3's. So let's see if you buy that. We're looking at this equation here. Every prime that occurs in a squared has to occur an even number of times because you have this prime factorization of a and then you square it. So the number of primes gets doubled. And 3 divides a squared. So it could be that there are no 3's in the prime factorization of a, but I don't see how. But that's why I pointed out that 0 is even. But a squared contains an even number of 3's. Now, on the other hand, b squared, 3b squared, sorry, 3b squared contains an odd number of threes. Do you see why that has to be true? Because whatever the prime factorization of b squared is, every prime occurs an even number of times. Then if you add a 3 to that prime factorization, now suddenly you have an odd number of threes. So what does this mean? Well, 3b squared cannot equal a squared, a contradiction. And we are done. So how did we do that? We got to this same place as we do in the square root of 2 proof, but then instead of arguing that 3 divides a squared and so 3 also divides a, which is what your textbook does, I just considered the prime factorization of these two numbers. And a squared, every prime that occurs in a is going to appear an even number of times in a squared. The same with b. But then when you multiply 3 times b squared, you're introducing either a 3 for the first time, that's 1, that's odd, or you're adding to that even number of 3's that's already there, making it odd. So a contains an even number of 3's, and 3b squared contains an odd number of 3's. So it's a different approach. I encourage you to look at the book and see which one you like best. All right, here we go. This says the sum of a rational number and an irrational number is irrational. This is a for all statement in disguise. Given any rational number and any irrational number, what this is saying is that the sum is irrational. So I'm using Q complement as the set of irrational numbers. So remember, Q is the set of rationals. I don't remember if we talked about the irrational numbers being the complement of the rational numbers. And did we mention that this was true, that the real numbers are made up of the disjoint union of rational and irrational numbers? A real number is either rational or irrational, and never both. All right, let's see what we're going to do. We need to negate this statement so we know what we're working with. We're going to say there exists some rational number and there exists some irrational number such that their sum is rational. So that's the negation of that for all statement. This says for all rational numbers R and irrational numbers S, R plus S is irrational. The negation is there exist these numbers such that R plus S is not irrational, in other words, is rational. So let's write this better. So, proof. Do contradiction. Suppose not. Suppose there is some rational number R and some irrational number S such that R plus S is rational. Okay, how did this give us something to work with? Well, R is rational and R plus S is rational. Since R plus S is rational, we can write R plus S equals A over B for some integers A and B. Oops, got too carried away. Likewise, R is rational, so R equals C over D for some integers C and D. Now, what do we have? We have R plus S equals C over D plus S, just substituting for R there. And what does this equal? Well, this equals A over B, because we're supposing that that sum is rational. Equivalently, S equals A over B minus C over D. So I'm just solving for S now in that equation. And we can say more than this. Let's get a common denominator. This would equal equals AD minus BC over BD. Do you agree? We got a common denominator of BD. So I needed a D for the A and a B for the C. Well, let's let M equal AD minus BC and let N equal BD. And note that both M and N are integers. Thus, what do we have? S equals M over N, and that's a rational number, a contradiction. What did it contradict? Contradicted this right here. We supposed S is irrational, and then we got all the way down here where we have S is rational, and you can't have both. So that's our contradiction. And we have proven this result, that the sum of any rational number and an irrational number is irrational. Pretty good to know. Okay, the last thing we're going to talk about is conditional statements and proof by contradiction. We have not really been doing conditional statements so far, and maybe you didn't even notice. But suppose you want to prove a conditional statement by contradiction. Well, the first step is negating what you have. So we would want to negate this conditional statement. And remember what that looks like. P and not Q. So when you do a proof by contradiction with a conditional statement, your first line is suppose P and not Q. And then you reach your contradiction and everything is fine. So let's look at a truth table to see why this makes sense. So I've started this truth table for us. Here's everything we need. P and not Q, well, true and false is false. True and true is true. False and false is false. False and true is false. So that's how it should be because it's the negation of this, right? So you can see that these truth values have changed. A contradiction is always false. Now, let's look at this implication. This is, keep in mind, this is the negation of P implies Q, and we're saying that we want to know what the truth value of this is. So, this implies that. False implies false is true. True implies false is false. The last two are true. Now, check this out. These are identical. What does that mean? It means these are equivalent statements. So if you can prove that this assumption leads to a contradiction, that's the same thing as proving P implies Q. And that's pretty neat. So we have a very simple example, and we have proven this before using a contrapositive proof, which is a good point, that sometimes a contrapositive proof will suffice. And our author says use proof by contradiction with caution. It's not the favorite type of proof. If there's a direct proof that's not too awkward or a contrapositive proof, you should try that. It's sometimes just clearer. It's more precise in some way. But let's do this one and just show how it would be. So we have if P then Q. We're going to do a proof by contradiction. So remember what we're going to assume. I'm going to say suppose not. What do we want to suppose? We want to suppose P and not Q. P and not Q. And you could have just gone ahead and say A is odd. That's what you'll say next anyway, right? And now you know what to do. And so what does A look like? A equals 2k plus 1 for some integer k. Okay, now consider A squared. We have A squared equals 2k plus 1 squared. That would be 4k squared plus 4k plus 1, or 2 times 2k squared plus 2k plus 1. Now what am I going to do? I'm going to call this something. And what do we know about m? M equals this thing in red over here. M is an integer. So we have, what do we have? A squared equals 2m plus 1, and a squared is odd. A contradiction, which I ran out of room. Oops. Okay, so how did that go? Well, remember we have to suppose P and not Q, and then we showed that it led to a contradiction. So we supposed A squared was even, but A is odd. If A is odd, we can write it like this, 2k plus 1, where k is an integer, and then you see what A squared looks like, and you end up being able to show A squared is even. I mean odd. So you have A squared is even and A squared is odd. There is your contradiction, and you've established your result. Okay, so that's all for now. Um, we can talk about knights and knaves, maybe, if you want to submit some solutions or figure that out. I think it's worth spending a little time on. It's just a good exercise for your brain. But you're ready to do the book homework. I didn't assign all of it because some of it's a little tricky and we need to keep moving. Don't want to get bogged down in some of these proofs that have multiple cases and take a long time. We need to look at other techniques. So do the assigned book homework, and then there's a Canvas quiz. I think it'll be 4 to 5 proofs again. Um, Not too bad, and maybe we'll look at them and make sure you know how to get started.